So I thank you all for coming out tonight to hear my talk on Perl Security. I'm Steve Flitman. My title at Xenoscience is Programmer at Arms, which is a not very veiled quote from a Werner Vinge novel. And the important thing about security is that in order to have security, you have to have defensive tactics. So a whole lot of what we talk about in computer security is essentially assessing our attack surface, which is the whole range of possible vulnerabilities that can happen and that our application or our system can afford to an attacker. And so one of the biggest issues is input data. And so a big problem in all of our Perl applications is that we're processing data. You don't always have control over where your script is running. If your script is very successful, let's say like a web script that does a calendar app or something like that, and it's going to run on a lot of servers, maybe it's going to encounter malicious input. And if it has not been written to expect malicious input, then it's possible for an attacker to gain control of the system with horrible consequences. And so you would rather not be the vector of that. And that's why security matters. And so careful handling of input data is necessary. And then you can prevent unauthorized access. You can prevent shell injection. And the term injection is sort of a general term in security of putting something in that doesn't belong. And so if you can inject a shell command, maybe you could gain root. Maybe you could then use netcat to send a shell back to an attacker who now basically owns your system. He can do anything. And that's the sort of like the prize for the attacker in any kind of computer security scenario. And one of the things they can do, which generates money, of course, is they can grab data, and the data may be very valuable. The identities of customers, of patients for a medical information system, and social security numbers, lots of valuable things which have actual monetary value on the black market. And then we have to worry about SQL injection, which is a technique where an attacker can put in information that looks like an SQL command or modifies an existing SQL command, and that creates then the ability for them to get data they're not supposed to have access to. And that way they can penetrate a system without having to have a login. They don't necessarily need to get a username or password because they can make your own software spit out the data. And I'll show you a small example of that. And escalation of privilege. And that's essentially the same idea as shell injection in that with escalation of privilege, you have a program which kind of like a crafted PDF file, which when opened by the victim, now it can take over the system, can install itself as a service on that system. And that's exactly what a botnet is basically large numbers of computers that have been suborned into running malicious code because these things can spread like email attachments and get all over the place. And so it's very frequently what they call a phishing attack, where you can have people open some kind of a statement like, here's a shipping notice, and there's a .zip attachment. I get maybe 15 of those a day in my email, and they're all garbage, and if you scan them, they're all Trojans. They're all malware, all directed, by the way, at Windows systems still. For the most part, they're exe files. And those are going to be systems which, or kind of applications which once they install themselves can now be controlled by a command system someplace out in the internet, maybe in Kazakhstan, but not just Kazakhstan. All over the world, there's malicious folks who are then controlling these botnets and creating lots of problems. And then denial of service. And DOS is certainly a very scary thing because with DOS is a situation in which your production server is being taken offline. And that's a situation in which there's a tremendous loss of profit. Customers can't reach your website. You can't transact business. And it's causing businesses to lose tons of money. And then the scariest scenario there is DDoS, distributed denial of service, in which there's lots of attackers, and that's one of those botnets, can be all directing traffic at your server. So now you have multiple levels of attack all coming at one server, which can't then handle all the traffic, and it goes offline. And that creates a lot of trouble. So the attack surface is all points which an attacker can gain entry, and there are basically the points of vulnerability. And so we talk about the inputs, and most inputs for a Perl script are going to be command line arguments, and and then for environment variables, especially the path. If you supply the wrong path to a script, if a script relies on calling other programs that are, especially using shell escape, and using programs that are supposed to be specific designed behavior, and then you put a fake version of the cat program, for example, trivial example. But then you could then imagine that the behavior of your program as a whole no longer works because the path has been changed to something that it doesn't expect. And URL parameters, or the values of forms for a CGI web application. And that's where most injection attacks come from. And so one good example of this is unauthorized access. So to achieve unauthorized access nowadays, what you need is basically to either supply the wrong password or to supply a password which will hash to something that's already accepted as a password. And that's a huge problem with an insecure hash. So hash functions are used all the time now to store passwords so that you don't have to store the password in plain text. And so I can have a system with a database where these passwords are hashed, where I can't tell what your password is, but you can get access to my system because your password, when it's entered, is hashed, and then the hash is compared to the value that's in the table. And that's very powerful, and that's a very old idea. That's how the original /etc/password file was represented. And then later they have the shadow file. So the shadow file still stores encrypted passwords. But the problem with this is that if you don't have a very good function, maybe you'll have a situation in which there could be a hash collision. And then you could supply invalid input, which matches what the computer thinks is valid input, and then bingo, you've got access to that account, which you shouldn't have. And so many older scripts rely on hash functions which are now known to be insecure. And so MD5 is an example I'm going to show you. NTLM is something that's used in Windows systems, and it's very insecure. And the rainbow table is an interesting notion. Some functions are, and some examples of this, are not hard to compute with modern software. In the past, these functions were thought to be very secure because they were slow. It would take, they thought, 1 million years to make 1 billion combinations for common passwords. But now with a rainbow table and with modern software, modern hardware, and like the cloud, you could have multiple servers running. You could calculate a rainbow table which contains hashes for all possible passwords using the character set capital A to capital Z, lowercase a to lower z, 0 to 9. And let's say out to, say, 10 characters. And so you could buy this rainbow table, you could download it, maybe it's a terabyte long. But that's not so bad. And not so crazy. It would take a long time to download it. But if you could generate it yourself, you now have a very powerful mechanism where once you have knowledge of what the hash might be, which you might get from sniffing web traffic, you then could find out what that password is by looking it up, doing a reverse lookup in the rainbow table. And then that's it, the person's in. So here's an example of MD5 hash collision. MD5 was at one time thought to be the Ne plus ultra of hash functions. It was thought to be a very powerful hash. It's now been replaced by SHA, and the SHA-1 actually has some insecurity too, so now they're recommending using better versions. So I have a system that uses a production server that's using SHA-512, which is extremely secure, and at least for now, until quantum chips come in and make everything insecure, I guess. But here's an example. There's two 64-character passwords, if you will. So we'll call them passwords. They're called message 1 and message 2. These were crafted by Mark Stevens, who published this last year. And they are both very similar looking. And so you could imagine that this could be something that maybe was produced by an RSA key or something, rather than something that you type in as a password. So it's a little bit of a contrived example because it's large, 64 characters. But these 64 characters differ only in 2 places, but they still are different passwords, if you will. And if you run the diff command, they're both, they're definitely different. It's clearly that they're different things. If you do the SHA-1 sum, which is a hash that gives you a large hash, you can see they're definitely different by SHA. But if you do the MD5 sum, they look identical. And then if you were relying on MD5 for a hash authentication of passwords, let's say, this is proof that MD5 is not secure and that you're going to upgrade your software. Lots of old software still uses MD5. And it's still part of a lot of protocols.
So that means you could get into a system using the second message, even though the password was the first message?
Precisely. So here's like a password that's correct. So I'm defining a, off screen there's a function called slurp, which reads a file, okay, into a variable. And so let's say that you'd call permit access with the correct password, which is message 1, and then it'll say, okay, access granted. It's very simple. It just runs MD5 hex and then gives you, does the password match what it thinks the authorized password hash should be. And then if you gave the invalid password, it would also print access granted because it would be exactly the same. And so that's proof of the fact that the MD5 hash is insecure. So new systems cannot use MD5. You have to upgrade, and it's better.
I have a question on that. So how did you determine, like if you had message 1, how would you determine message 2?
Right. You have to read Mark Stevens' article.
Okay.
So he gives a method of generating pairs of 64 character blocks, which will fool MD5 because they'll hash the same thing.
Okay.
So the way you do this as a real attacker is you'd have to sniff network traffic, look for MD5 hashes, then go backward. And then you can do some amazing things. You can just Google an MD5 hash. So there's one exercise that we did at the Black Hat conference where we took, there was a MD5 hash was floating around that was someone had seen pass through on Ethernet. You know, they saw it come through in a Wireshark packet. And you just copy that, paste it into Google, and Google said, oh, it was this famous picture, you know. And it was the hash of the picture. And then you could tell, okay, now you know more about that conversation, and then you could take it from there. But when you use a tool like Wireshark, you're looking at network traffic.
Right.
You're going to see the login exchange, you know. And so if it's SSL, there's a little bit of veneer of security there, but we know SSL can be suborned also. That's been Moxie Marlinspike showed that SSL has lots of vulnerabilities, and not the least of which is the current certificate system with the CA roots, and big money there, and VeriSign and Thought, of course, because they're in business to make money, but if their root certificate is suborned, is somebody manages to break in and grab it, then all the certificates are bad. Or worse, they can issue now new certificates that, unless your system has been upgraded, it thinks they're valid. Right. And that's a very bad problem. There's also man-in-the-middle attacks where you can you could fake an SSL exchange, do the key exchange, and then now you're looking at another website that looks like your bank's website, but it's not your bank. Right. And you're telling them to transfer money, and they're saying, okay, we'll transfer all the money. How about that? So this is a very trivial example, but the notion is that password invalid should not say access granted. It really should be a different result come out of the MD5 hex hash function. So this is a simple example of shell injection. So here's a very trivial program which no one should ever put in production, where you take a command line argument and you feed it right into backticks. So it'll run that as a shell command, and you'll get things you shouldn't be aware of, like what the different users are on the system. So at least you don't get passwords anymore, even encrypted passwords from password file. That's in the shadow file, which you're not supposed to have access to. And then eval injection is just as bad. So here you're running eval, then taking a command line argument and putting it directly into eval. So a bare eval function will basically run anything that looks like good Perl. And so I put in sort of iffy Perl, like a one-liner kind of Perl, where I'm opening the password file, and I'm printing every line while the file operator spits out lines. And so it gives you the same output. And there is a way to do this when you need to put information, you need to use eval that's safer, and surprisingly it's called safe. And it's part of the Perl distribution. So you can use safe to create a compartment which will eval things, and you can eval arbitrary functions, but you tell the safe compartment what you're supposed to allow. So don't allow the open command, don't allow that, only allow math functions, for example. If you're going to use eval to do a rudimentary calculator, let's say, you're going to write like a reverse Polish calculator program, and you want it to be able to run. So there's a right way to do that. And this is to show you a wrong way to do it. And then there's SQL injection or SQL injection. And this is a serious problem because this is sort of the workhorse of all business software essentially nowadays. And then the DBI, which is wonderful, is Perl's method of having basically abstracted access to any database system known to man. And it's incredible. It's a way that you can basically convert anything. And even there are modules for DBI called DBDs for legacy systems, like really old IBM systems and databases which are actually not databases at all, but are flat files. You can read with, and you could do select statements just like any SQL database. But this is sort of the basic function which everyone has to write in order to execute DBI query. So I just put it in a function to make it easier. And what it does is you put a query in. So the query could be select star from users. And then when you put it in, you're going to prepare the query. If that doesn't work, then you'll get an error, then you'll die and get a error report. Then you're going to execute the query. And then if that dies, then it also comes out. And then you get the statement handle. And the statement handle, after you call SQL, the statement handle will grab each row, and you can call the function fetch row hashref, which basically grabs a hash reference to all the fields that are in there. And then I wrote a little subroutine called dump hash that will show you what's in there. So when you do this sort of select statement, select star from users, where username equals $Q in quotes, so Q there is coming from the command line. So that could be like asking a particular, I want information about a particular user. When you do that, you're going to get, and you should really be getting just a single response. This is a little contrived because it looks like it's going to be expecting a number of responses, but it should really only be getting one response. And that one response would be the username that you requested. And then when it comes out is, then it'll look like when you print it, field equals value, space, field equals value, and so on. And that's your hash dumped into text. That's what dump hash does. So an example of that is if you use I use Postgres, so I use the Postgres command line program, and I'm doing select star from users. I would see, just the three records that I've put in the database so far in the users table. There's a user supervisor, user Mary, and a user Steve. And then these are IDs. And there's a nice feature in PostgreSQL where you can assign for an index field, you can assign something called serial. So it'll just keep generating from a sequence a new ID number for each record. So you don't have to think of what, you don't have to do a test on the database, like a read from the table, what's the max ID before you insert a new record. It just increments a sequence, which will be important for you to know later. And then if you put in just Mary, you get the expected output that, we got ID 1, password, and XYZZY is supposed to be a hash. Rather than writing something huge that was going to go off the end of the screen, I thought I'd just put something well known to all people in this field as a moniker for a hash, And then if you put something contrived like this, where we take Mary, we put a quote after it, and we say, or 1 equals 1, dash, dash. That's SQL injection. So what's happened here is that this expression has been dropped into the string for the query. and now it's saying the wrong thing to the database backend. It's saying, I don't want Mary, I want anything that matches this expression, and surprise, surprise, 1 equals 1. So guess what? You're going to get every record in that table is going to be pumped out. And so you see everything. So you see things you're not supposed to be seeing. And that's the whole holy grail of SQL injection, getting data out of the system that is not intended.
It's like a classic XKCD comic about little Bobby drop tables.
Oh yeah, it's beautiful. That's right. So I have an example for you about drop tables. So it turns out that DBI is smart and Postgres is smart too. So the Postgres, the DBD, which is the module, Perl module, which allows the DBI to interface to a Postgres system, it doesn't let you put in multiple commands when you prepare a statement. If I used dbh do, where you could throw in any kind of text, it'll just run through with the semicolon separator, you could drop the table. But there's no way to make a select expression drop the table. Yeah, at least in Postgres. In Oracle, there's some kind of eval kind of a command, like eval SQL, which allows you to do some arbitrary things, which then get the result into your select, and that can be dangerous potentially. And I think there's something like that in MySQL too. But here's an example. So this one doesn't work. So trying to drop the table as part of the SQL injection attempt to be even more malicious than stealing the data is to delete the data. So you're not going to get that. But you can have side effects. So this side effect, you use next val, which is a way, you'd have to have some kind of back-end knowledge. You'd have to know that the sequence for the user table is called user ID SEQ. But if you knew that, you would then be able to not only suborn the whole system because this is true and you get all of the records out just like or 1 equal 1, but you've also made a change. So you've influenced what the next record ID number is going to be. So now if you select what is next val, it turns out it's 5 now, and it shouldn't have gotten that high. But because you ran this, it was probably 3 after this insert, and then it was 4 when you did that, and now it's 5. So you've gotten to a point where you can manipulate the system to generate an internal ID code, which might be very important. The ID code might be an index into a roles versus a permissions table. And now you can basically know that if you're the next user registering for that system, you will have a particular fixed ID. And potentially that would give you an extra advantage in getting into that system. So it's definitely possible to have side effects that are unintended from running just a select query. And then you can do even worse things. If you know a lot about Postgres, you might be able to list all the databases that are in the system. So this database cluster contains test, which I made, but also contains template 0, template 1, and Postgres. And those databases I wouldn't have known. And you see how I did the union. So union has some limitations. You can't get out of the SQL injection with union anything more than the fields that are normally going to be there. So you'll get an error. So while I was playing with this, I couldn't select more than 3 fields because it's only 3 fields that are in the first part of the select expression. And so because a union is supposed to be between 3 like queries, and then it'll make the union of the two queries. But what comes out of it is because the DBI doesn't realize and trying to do something sneaky, is that these files are listed, or these values are listed in the places and with the keys in the hash that comes out of that with the original keys of the original query. So that's why it says ID equals, password equals, username equals. But those aren't the field names I used in the union. In the union, I used .con limit, .name, and .ctype. And so those come out. And so that's an interesting issue. But someone who's looking for information like what other databases are on this juicy server, this is how you'd get it using SQL injection. And the same with union, you could do something even more nasty. You can get the server's private key. And that's an interesting issue with the PG read file. So Postgres, I've used Postgres for 10 years now. I think that's a really great database system. I think it's better than Oracle. I think it's better than MySQL. It's more scalable. It's free. There are a lot of nice things about it. And it's very actively developed. But everything has security holes. And when you provide functions that are supposed to be for convenience, that like PG read file, maybe you get bad things come out. And so in PG read file, at least they're thinking a little bit about security because that function will not accept an absolute path. You can't say /etc/password there. But you could say server.key because you know that the server.key is stored in the Postgres database cluster. And in that cluster, which is under like varlib pgsql main, you'll look in there, you could find your private key. Now you could you could authenticate remote access potentially if it was turned on to this server, and you could now send queries, from the McDonald's down the street, which you're not supposed to. And that obviously is not the intended thing for the owners of the system. But then also you notice how, again, using union, it comes out in the slots that were prepared for it by the original query. So the attacker is constrained that way because they can only put things in because they can't control, until they take over the server, they can't replace your script. So the script is saying that the query is always going to start with select star from users where username equals quote $q quote. So you have to have something that's going to fit between the quotes. And you don't want a syntax error, which is why all of these attacks all end in dash dash. Dash dash is like the pound sign in Perl. It introduces a comment. And so that gets rid of the final closing apostrophe or single quote. And but there's a hidden, because it's putting in there, you got to provide this closing single quote here. And then the unions, for those type of attacks, here you got the single quote, and then for the union, you see this single quote there, because it has to put it there. And then the dash dash at the end is so that it won't create a syntax error because it'll see the final quote on the end of the line, which doesn't belong anymore for a valid SQL statement. So how can we mitigate this terrible mess, and how can we have nice things again? One of my favorite lines from Black Hat, I always start every talk there, starts with, "This is why we can't have nice things," which is rather sad when you think about it. So a very nice mitigation strategy is taint checking. Taint checking it comes from a long line of research in computer science looking for ways that you could tag data. And you could tag data as tainted if it comes from certain sources. So Perl will automatically turn on taint checking if it sees that its script is setuid or setgid. So that's a situation in which you're running the script, and as a particular user, let's say I'm running as user Steve, and then the script is owned by root. And if it's setuid root, then the script runs as root with full root privileges. So it's doing something for me, like it's going to format a drive or something. It's going to do something high level that I'm afraid to do as a mere user, But maybe that's a bad thing, because if it's insecure, then somebody could misuse the script, and that's why taint checking is helpful there. Otherwise, you put the $T flag on the command line or on the shebang on the pound exclamation line, and you're able to get taints to turn on. And when you turn on tainting, you can then do some better security, basically, because it's going to provide you with an extra level of checking. It's going to make your program run a little slower, but taint checking does seem to be helpful because it can catch scenarios where maybe you forgot, maybe you're tired, but when you wrote the code, you made it possible for an attacker to put information directly into something in your program that you don't want there. And so the tainted variable cannot be used as an argument to a built-in function. And so there's a method of untainting. So here's a demo where shell taint.perl. So here's where you put the -t on the shebang line. And so when Perl sees this, it'll run itself with that flag. And then we try to do the same thing we did before for shell injection. But now, if you try to put the information in, you get an error. So you get a runtime error, insecure dependency in backticks. So that's very nice. So that at least protects you from spitting out all the users on your system, which you're not supposed to do. And then this, of course, is a very trivial example. But a little more fancier example. So here we're going to try, we're going to be very good Perl programmers. We're going to use strict. We're going to use warnings. We're going to pull in the command. We're going to say, okay, I'm not going to use command directly. I'm going to use mung, and I'm going to change the value that comes in. I'm going to substitute it and get rid of multiple spaces, because maybe they're malicious in some way. I don't know. Maybe it's a buffer overflow attack. Someone's going to run the command with 900 spaces on it, and then at the very end, the particular thing that you want the machine to do. When you do this, this doesn't work either. The tainting mechanism, the taint has traveled from the command variable to the mung variable, and you have not done enough to untaint it, so it's still tainted data. So backticks won't run it. Does that make sense? Yeah. This is a very powerful thing. So the idea is that tainting it travels from value to value, and quite a few things can be tainted. I'd refer you to the PerlSec man page, but things like hash keys, I think, are not tainted, but hash values are. So you could have a hash or an array where some slots are tainted and some are not, which is interesting, depending upon where they came from, how they were assigned into the hash. And then the taint follows things until you untaint. And you could use there's a module called untaint to directly remove the taint flag from a scalar variable. You could also, and untaint can untaint arrays and untaint whole hashes too. And there's a taint module also on CPAN, which is very nice, that will allow you to inspect whether or not a particular variable is tainted. You can just say if this is tainted, rather than doing this horrible eval with join and funny sub-expressions, which is another way of demonstrating that a taint exists on a particular variable, because you'll create an error and then you'll capture the error from an eval. So that's how the isTainted function is implemented. Of course, you could implement it directly in C and put it as an XS, but that's kind of going against the grain, right? So this is how you untaint. So first off, you have to set the path. If you don't set the path, then when you try to run backticks under taint mode, it'll say, wait a second, the path is tainted. So you have to set it to a known path which is safe for your system. So I'm not going to let anything run except things that come from /bin or /user bin. We'll get the command, and this is the recommended method of untainting. I'm going to read the command with a regular expression, which we now know a lot about, thanks to Doug. Thank you. And I'm going to capture an expression from it. This is obviously very trivial, but because it's going to still allow me to capture something malicious. But I'm going to capture this expression, put it in here in $1, and now assign it back to command. Well, that untaints. And so this is the recommended method for untainting a variable. You've extracted the information which is safe to use. You presumably you scanned for bad meta characters, things that are going to send your output to /dev/null or something bad happening, or email it pipe send mail to maliciousbadguy@badguy.com, And then now you could say this, and then this is another example like the SQL injection where there's a fixed part of the command that's actually going to get sent to the shell, which you don't have control over. So that's the cat. And so you don't have control, the first part of the thing is going to be cat, but if you supply the password, well, it's going to print whatever that file is if you supplied the /etc/password file. So that's why it prints all this. But at least this text was untainted by the untaint mechanism here, so that you knew that it was pure. So now you can have a method of detecting tainted data. You can check your inputs, make sure that they're safe, and then presumably at some point in here, before you start using this data, you would now see, is it semantically pure? Is there something about it that's not cool, like it's going to try to print the password file? And so at that point, common sense has to pop in. So all tainting does for you is it catches unexpected mistakes, things that you weren't thinking about. And sometimes it really saves you, because you may discover something that you didn't realize that that the value that was still tainted by the time that you got to use it in a call to a system command. Something important like backticks, or if you're going to call something like sysread, for example, things like that. So how do you defend against SQL injection? The answer to this is the DBI allows something called parameters. And the parameters are very nice. So we've made just a couple changes here to the previous program. And all the programs are available on my website, by the way, under zeoscience.com/perlsec. We've added the @args argument to execute so that when the statement is run, it will bind the arguments which were passed in to the SQL function. And so SQL function, instead of saying $q equals shift, now it's saying $q and @args so you can have multiple function parameters. And so when we connect to the SQL function, when we call it, we have a query, select star from users, where username equals question mark. So that question mark is for a parameter binding. And so you can have multiple question marks, you do as many as you want. And then you close that, so this is one piece of text, and that's $q. And then for args, we're going to put $q over there from the command line, from @argv. So now, when you put this in and you say, I want information for user Mary, Mary will not only will it only Mary go into the question mark, nothing else can fit appropriately without destroying the syntax of the SQL command. So that's going to defeat the SQL injection. So you can put in Mary, and it works. You can put in our contrived expression, or 1 = 1, and it gives you no output, because at that point, what you got was this expression was put into the parameter, and then it doesn't look like a command anymore, and so you get no output. And you could do the same thing with the union type things, so you get no output at that point. So what's happening is that you're putting this evil expression in over here with the question mark, and then once it's put in, it no longer looks like something that matches anything that's in the database. So it's actually looking for a username with those characters or 1 = 1 in them. And then the initial quote there gets quoted by DBI. DBI will turn single quotes into 2 single quotes, which is SQL for like a backslash quote. We're not supposed to use backslash, we're supposed to use two quotes, which is a little strange, but that's SQL. So that's how you defeat SQL injection. And it seems to be the very best thing you can do is to use the parameters and binding. You can get fancy that it'll actually accept name parameters too. And then you could pass a hash, and it'll give you, so you could have parameters named like :x and :y instead of all question marks. If you had a very complex expression, and you're getting cross-eyed trying to count all the question marks. And then escalation of privilege we talked about, that using the setuid and setUID scripts is, of course, very dangerous, because you could be tricked to run something else, and it'll run as the set user. So, and that's usually root. So people don't set UID to a simple user usually, unless they're trying to do something tricky with that person's home folder maybe. If root is to accomplish something, you can use a trusted daemon. And so this is actually a very nice kind of a design pattern, if you will, for Linux systems, especially where you've got to do system resources or do something fancy. So I have a system where every now and then I need to make a change to postfix. Postfix is running. I have hundreds of users. I want to update the relay that table so that postfix will relay email for them. And so I have to restart postfix to do it. But if my code, which is running under the web server, under Apache, if that code were to try to sudo or something like that to make postfix change and to reload its table, that would be an error, because the Apache cannot run as root, and only root can do that, and can do that. And you can't get, there's a way to do sudo with Apache, but it's a mistake because it leads to a security hole. So a much safer thing is what my script does is it simply puts it touches the file in /temp, and then I've got a daemon running which sees it, and when it sees that the file has been been updated, it then reloads postfix. It just sends the command for me. So it's running in root space, and my script is running on the web server. So it's completely isolated. So you have to achieve some sort of isolation. And then a good example of how to do this in a nice way also is running over a socket. So something like Postgres itself, the Postgres system, runs on a socket. It's waiting for commands to come in. It could be a local socket, or it could be a port for a remote server to send commands to it. But it's isolated. So that way you're not going to have a problem where you're going to be directly manipulating the table from a script, for example. And so you get some isolation there, and that provides better security. And then if you're really in trouble, if you could just make a root module, but make the root module very limited. It only does one thing. It's 5 lines max. So there's less likelihood that you're going to put a lot of function in there that could then be misused by someone later. And the root script can drop privileges. So if you go to the PerlSec man page, you'll see there's a very nice description there of a simple way that you can fork. You can do something as a child process that may be less secure. And that way, when root drops privileges like that, it can't be misused. Because now it's running as a child process to do the work, but the child process has only the permissions it needs. And so that's very nice in a fancier environment like SE Linux, where there's lots of fine-grained permissions, for example. So you could set all those up for your child process, tell the child process, all right, now you're going to go off and do this project for me, but you're not going to be able to do anything else. You're not going to get out of your box. And you could cheroot it too, so it can't access the rest of the file system. So denial of service, we had talked about like the flood of network packets from multiple sources, that's DDoS. And this doesn't have to be a very obvious sort of thing like 100 browsers attacking your server. It could be something as simple as a program that is malicious and will just run an infinite loop. And it'll just use up resources until your system crashes, goes out of memory or something. So a good example of that is reading a file that never ends, like /dev/random. You can prevent these sort of things if you're very careful, like when you use the safe module, for example, if you have to run arbitrary code, which is already a questionable design decision. Sometimes you have to do it. But when that happens, at least you can specify, okay, the safe code has to do these sort of things, and I can also I can run the code in a compartment where I have an alarm outside the compartment, a timeout. So, code that takes 10 minutes to run is not normal. That should not, there's something wrong going on there. And then you could bomb out of that and say, okay, this was probably malicious code, I'm not going to run it again. And then for this situation, the flood of network packets, that's a hard thing to defend against. So there are companies like Radware that make a box that actually is a denial of service preventing box. Kind of like Barracuda has their modules, and they charge an arm and a leg for it, of course. But it's what you got to do because for a large corporate installation, you have data that's valuable, and you have systems that are valuable that you can't have any affordable downtime. It's painful enough to get maintenance downtime, right? So that's a big issue. So one way to accomplish this is what's called stateful firewall. So I've written a program called ActiveBlock, which basically does this using IP tables. So Linux systems can have, you can set up all sorts of rules for how to handle each packet that comes in from the network interface, or from multiple network interfaces. And so a very simple thing is ActiveBlock. It runs as root because you can't manipulate the IP tables unless you're root. It sits and looks at log files, and it just waits for a log file to be updated. So it looks at auth.log on Ubuntu systems or Debian type systems. And what it sees is that there's been an SSH attempt with a bad password and what IP address it came from. 3 of those attempts, it could be me, I'm late at night, I had too many beers, and now I'm having a hard time remembering what my password is. In this case, it could be a bad guy. And then once there are 3 bad attempts, it will lock out and it'll be locked out, so that particular address will be blocked. And what's interesting is that from the attacker's standpoint, your server just disappeared. You're dropping packets silently. You're not actually having the server, the attacker, getting any kind of feedback that they're getting through, or they're not getting replies like bad password, and then allowing them to continue a brute force attack, because bad guy could be out there, and let's say he gives you 20,000 different passwords. He could just keep hammering your server until he finds one that finds a password that works. Especially if you were lazy and had very small password. XYZZY, don't use that. Yeah, because when that happens, what do you say? XYZZY, nothing happens, right? But at that point, so that's why you use IP table. And IP table can forward packets, but also could drop them. And when you put the IP table rule drop, it's very fancy. You're trying to attack, and all of a sudden that server doesn't respond anymore. It's like that port disappeared, or the whole IP address for the server you were attacking is no longer there. And so this is what Steve Gibson calls you've stealthed your server. I love that. So it's very cute.
But to re-enable that, is it like a timeout or something?
No, you can. The problem is that a lot of the IP addresses that you're blocking, maybe they're spoofed. So you don't know that what's coming in necessarily, that you're going to block that until the next boot, basically, then you get a fresh IP table. But you can inspect the IP table that ActiveBlock creates, and you can list what's been blocked, and then you can reallow any IP address. So
like in the case where you...
Yeah, when I'm blocking myself. Yeah, then I have to use log me in, go in around my NAT. I have to go in from inside the office to tell the server, wait a second, that is actually okay. That's my IP address from this hotel room where I've been sitting, you know. So best practices: use taint checking. Never use user inputs directly in eval or a shell command like backticks or system. Use DBI parameters because you'll get sanitized input to your SQL expressions. People won't try to twist your syntax and use it against you. And you'll also get quoting, appropriate quoting, which turns out to be not easy. There's lots of weird corner cases with quoting for SQL. And you don't want to roll your own. You definitely want to use DBI because that's what DBI is for. It's an amazing piece of software. And then this is an interesting thing. This is a scary situation, which is an easy thing that happens in production systems for the web, where important files like a list of credit cards that have been accepted by a particular PHP script I won't mention the name of exactly, but they're sitting in plain sight if you know where to look. You know, /admin /data /lib /creditcards.php, and then bingo, you got them. And so there's no reason that the data ever had to be in the web hierarchy, you know. But if it's accessible, then the web server, usually Apache, will give it to you. And so there are times when you don't have a choice. There's some issues with permissions, which are hard to deal with. But usually you can keep these things for your scripts outside. The scripts themselves, it would be nice most of the time to keep the executable code out of the web hierarchy too. And there are some nice systems out there like Mojo-licious that let you do that kind of keep things out and sort of create like a virtual server which is running and looks like a web server, but doesn't have any actual htdocs folder for somebody to get into and cause trouble. Use strong crypto. And the most important thing, which is really hard for very intelligent people like yourselves to keep to heart, is don't roll your own crypto. It's amazing how many people have gotten in trouble this way, because you always think to yourself, well, you know, especially, let's say I'm going to make something that no one else can ever break this code because I'm not going to tell anybody how I'm rotating these registers, you know, and then what you end up is reinventing ROT 13,
Yeah,
you know.
double ROT 13.
ROT 13, yes, especially don't use ROT 26, which is the same thing, it's idempotent. Yeah, so that's the issue. So the other problem is that crypto is actually really hard to do right. I'm no expert, but when I go to the meetings and there are mathematicians there who explain how hash functions are supposed to work, how the AES is supposed to work, for example. This is AES, Crypt Rindell. Those ciphers are the product of years of research to do them right, and there's all sorts of fancy tricks in them to make them hard to break. And so you can, because they're all free, basically lots of good crypto is out there, and it's free of charge, it's open source. You can use it, and the beauty of open source is you can see that other people believe that it's good too. So you build your product on and do your development using those building blocks. You're baking good security in right away. And so that's why I love these CPAN modules. Digest SHA has all the great secure hash algorithms, and it has MD5 too, I think, but you don't have to use MD5, please don't. There's even questions about whether it's safe to use it for making a file cache where you grab files. There's some issues with MD5 even there. Crypt Rindal, of course, if you have to do, you can do AES, and you can do AES with 256-bit keys, so big keys. Always use big keys, that's good. Session token, I just discovered while putting this talk together. Session token is fantastic. It basically will create a token for a session or a password for limited use, so it'll create a new password. So this would be great for your system where you've got people who have forgotten their password, which is a huge security hole, by the way, and that's how attackers got into Yahoo, is exploiting the feature of, I forgot my password, can you mail me a new one? You know, and they were able to figure out the back end of that and managed to get passwords that were authentic to get into someone else's account. And so a session token, you can generate nice, reasonably random passwords. And it uses a truly random source like /dev/urandom, or on Windows it has there's a quality random number source under Windows XP and later. And then I like to use this. So my production system now is using auth passphrase salted SHA-512, which is a system which will generate a SHA-512 for a password and a salt. And the salt is another little piece of binary which must be provided in addition to for the password, otherwise it won't decrypt, or it won't match. And so a salted hash is even better because while you could generate a RAM, with your rainbow table, you could generate a terabyte of possible hashes. Not with SHA-512, you'd have to generate a petabyte of possible hashes just for 8-character passwords. It would be huge. And nobody's going to do that. That happily is so far outside of people's capabilities. But next year there'll be petabyte drives, and then they'll be in trouble. And then somebody could, evil.com will sell you a petabyte drive which has a rainbow table for SHA-512. So hopefully that won't happen anytime soon. And then it gives you the salt also. So you get 2 long hashes which you then store in 2 separate fields in the database. It is legit to put them in the same record in the database. So cryptographically, it's secure from a researcher's standpoint that it doesn't look like it creates a problem to store the salt with the hash, because they're both fairly secure. You still have to have physical security. You don't want someone walking away with your hard drive. But even if they had that, even if they stole that, they still would have a very tough time recovering the plain text password. But watch out for log files. If your log files log every URL parameter, maybe they'll catch pass equals XYZZY, and that would be bad. And so you got to be careful about script permissions also. That the permissions that a script runs under really define what it can do on a system. And so that becomes a big problem with scripts that could be called, especially by the web server. So anything like Apache or IIS, for example, under Windows. No security through obscurity. You never have a system where it's not open to inspection, in the sense that other programmers should be able to vet what you do and see that it does make sense from a security standpoint. Because if you hide it, it won't work. And so this is why things like electronic voting haven't taken off, because Diebold Systems has been very cagey about how their systems work. So a lot of people are afraid to use them, and that creates a lot of problems. And I think that eventually they're going to come around. I think that eventually there'll be a lot of manufacturers of voting systems, of ATMs, for example, who will come to embrace the notion that if everybody collaborates and knows that this is a secure system, it's less likely to be broken into. But when you try to hide the details, someone will figure it out. And then password policies, I think everyone talks about this. The best thing I can distill from what I've read is that 8 characters has got to be the minimum, because it makes it hard for a trivial brute force attack. Mixed case, at least, because that expands the search space for a brute force attack immensely. When you add another 26 symbols, that's good, if you distinguish between uppercase and lowercase. And then every 60-day changing. So I think that there's lots of different policies out there. If you change them, any policy that says must be changed every n days is a good policy. Any policy that doesn't have a line must be changed is a bad policy, because clearly it's possible that someone could guess your password. So a great example of this is that everyone, myself included, we use the same passwords in every website because you can't remember 15,000 passwords. So there was a password I used for my PlayStation, and PlayStation got hacked. The whole PlayStation Network, they took it down. And sure enough, somebody tried to get into another account with the password I used for PlayStation. And so it was bad because it was a good password too, so I couldn't use it anymore. So I had to change it on everything. And then when I can't remember how to get into it, some website like GitHub, I have to think to myself, well, did I use that same bad password? And sure enough, I did. I never changed it. I have to go look for it. Wow.
Biometrics?
Yeah, biometrics is it's a topic for a whole other conference. It's such a big field. The biggest problem with biometrics is that I don't want to have a certain body part necessary for entry, because then someone will try to steal that body part from me.
I was going to say, I read an interesting article this week that said biometrics should be used as usernames, not passwords.
Yeah,
That's
I
interesting.
read that same
I like
article.
that.
But what's interesting too is, like, I know they've already figured out a hack around for the Apple thing, but Apple did have an interesting idea where the fingerprint actually had to have blood flow.
That's interesting. So at least that way you couldn't cut off someone's finger and use it.
Exactly.
Yeah, I like that.
Next step and synthesize the blood flow.
Well,
Yeah, you have to perfuse that finger.
Yeah.
It's nasty.
Yeah.
That's the problem with biometrics. There is hope for DNA reading devices are coming. They're not far away. There's a system from a company called IonTorrent that can read an entire person's full DNA, which is 3 gigabases, in 12 hours for $1,000. And so this is getting cheaper and cheaper and cheaper. So you could imagine something very simple that could read the DNA from some skin cells, see and get a megabase. So something which is a million different bases. And each base is 2 bits of information because there are 4 bases. And if you get that information, you could use that for like a DNA lock, you could imagine, or biometric for entry, and that would be fairly secure. I mean, someone could still try to steal your fingernail clippings or something like that, but I think that it's possible that you could make it smarter to avoid that kind of a hack around. And so I think that sort of technology will be really amazing when that comes.
There's also the facial recognition technology.
Face recognition, retinal scans, the iris pattern, iris scan is pretty good. Iris scan is nice because you're not actually letting a beam into your eyeball.
Right.
It's just scanning the outside of the iris, which you can see my iris right now, so it's okay. But that kind of thing, I think those are interesting. But the biggest problem with a lot of those things is what if a person suffers some kind of injury and now their scan is wrong,
Right.
and the iris changes too. It changes with mood.
Forgot my eyeball.
Yeah, forgot my eyeball and get emailed a new eyeball. Would that be great? I thank you for your attention. Yeah, that's great. Thank you very much. Glad you're present.